Hello, everyone. Welcome to Special Relativity 006. This is Billy Younger again, and this time I've got a kind of interesting problem I want to solve for you, just to show you some neat geometric results of what happens when something is speeding by. Specifically, we're going to deal with the Lamborghini Aventador. Excuse me, Aventador. I think is probably the proper pronunciation, Aventador, but it could be Aventador. We're also going to do a compare it to a Volkswagen Beetle, like a 1965, 68 era type Beetle, not the Super Beetle, which had a curved windshield, but the Beetle, which had a flat windshield, which was quite steep. So let's get cracking on solving that problem. I'm going to turn it to share the screen so you can read the actual problem that we're solving. So here's the problem. Volkswagen Beetle has a length of 4.08 meters, a height of 1.55 meters, and its windshield is inclined to 60 degrees. I'm going to record that data, of course. Volkswagen, you might notice that Volkswagen is spelled with an E after the G, not an O. Sadly, I never put that together until today, so that was pretty awesome. So the Volkswagen has a length of 4.08 meters. It has a height of 1.55 meters, and it has a inclined windshield at 60 degrees above the horizontal. The Lamborghini Aventador, the Lamborghini Aventador, uh, which I'm going to just call Lambo because it's bad enough that I just learned that Volkswagen had an E in it instead of an O. The Aventador has a length of 4.78 meters, a height which is considerably smaller than the height of a Volkswagen Beetle. It's 1.136 meters, and its windshield's inclined to a slight 22-degree angle, roughly. Okay. So in part A, what we'd like to do is find out at what speed must an Aventador travel so that its length appears to be the same as the length of the Volkswagen Beetle. So the Volkswagen Beetle is like 4.808 meters across. The Aventador is 4.78 meters. So we'd like to compress it till it's just as long as a Volkswagen Beetle, and then look at it and see, whether it looks more like a Volkswagen Beetle then, or if it just looks still like a bad car, like an awesome car. So I'm going to make use of some other pages where I found schematics of these, and that'll come in handy. But then in the second part of part A, I'd say, I asked you, what would it look like? So I'm actually going to take some JPEGs and then reduce them by percentages, and it should give a fairly accurate representation of what the vehicle will look like, other than colors, because I didn't take into account how the Doppler shifts would come into play. And then part B, it says at what speed must the Aventador travel so that its windshield is inclined at 60 degrees like the Beetle's? What would it look like then? So let us get started. I'm going to stop sharing my screen, and I am going to start sharing my document cam. And in part A, like I said, we're wanting the Aventador to be as only the length of the actual Volkswagen Beetle. As you can see, I've already got the data written down here. So this is problem 6. And of course, in Relativity 005, we're doing problem 6 because we're ahead by one number. So in part A, what we want is the length that we see to be equal to the length of the actual Volkswagen Beetle, which is 4.08 meters. That is not the proper length because that is the Aventador flying by us. So we're measuring it as it passes us by and is moving with respect to us. So L is equal to 4.08 meters. Now we know that in fact the proper length, which is what you get if you were riding in the Lamborghini, so that the Lamborghini is not moving with respect to us, that's actually equal to 4.78 meters. And we know that L is equal to L0 over gamma, where gamma, of course, is 1 over the square root of 1 minus V over C squared, which is also equal to 1 over the square root of 1 minus beta squared, which is what I like to use. Makes things a little bit easier. So that's a V over C in there. I'm sorry for it being so small. You just got to remember that gamma is greater than or equal to 1. So with that in mind, we should be able to work out what gamma is and then use gamma to find beta. So it turns out from L equals L0 over gamma, we get that gamma is equal to L0 over L, which of course is 4.78 meters divided by 4.08 meters, which obviously is going to give us something bigger than 1, which is what we expect for gamma. When I carry out that division, though, we can find out that gamma is actually equal to 1.172. So I carried 4 sig figs. We're using 3 roughly, so that's actually only 1 off, but that's okay. We also found way back, I think it was in special relativity 001, but it might have been 002. We found that beta is equal, yeah, it was actually in special relativity 002. We found that beta is actually equal to gamma squared minus 1 over gamma, so that can save us quite a bit of trouble in calculating the velocity. So we're going to take the square root of 1.172 squared. After we subtract the 1 from it, we'll take the square root and then we'll divide it by 1.172. And that will give us, in fact, a beta of 0.5210. Again, I'm keeping 1 extra sig fig. Now what this means is V is actually equal to beta times C. So V is equal to 0.5210 C. So that's one way of expressing the speed. Of course, you could also write 0.5210 times the speed of light, which is 299,792,458 meters per second. Again, I'm carrying a buttload of extra digits just because I like memorizing these numbers. And when I do that, I end up getting a 1.562 times 10 to the 8th meters per second, which is a big number, but to give you some perspective in miles per hour, that is in fact 349 million miles per hour. So pretty fast, I would say. That's our answer to A, part 1 anyways. Now, what does it look like? Well, let me take a second to share my screen again. So I'm going to share the screen with this one. And what I'll show you is this right here. So this is the Lamborghini in the normal scale and the normal size. And if I'm traveling at, I said 249. That's a typo there. That's supposed to be 349, not 249. I apologize for that. I will type that up in the document before I actually put it on my Google Docs. So if anybody wants to email me and get a copy, they can. Now, what I've done here is actually contracted it by basically the percentage. And the percentage, of course, would be 1 divided by 1.172. So if you take 1 divided by 1.172, you'll get about, if I remember correctly, it's about 85.4%, something like that. So I basically went in and clicked on this. I clicked on that and then did, actually, it's not giving me the setup that I came up before, but basically when you click on this, it'll say size and position. I clicked on it and then I unlocked the aspect ratio. If you lock the aspect ratio, then you're just going to shrink the whole thing vertically and horizontally, but we're traveling horizontally, so only this dimension should be compressed. So I went in after unlocking the aspect ratio and typed in 85.4. Let me double check that number since I don't see it on my paper. 1 divided by 1.172. Yeah, it's 85.32%. So 85.3 is what I actually did. 85.3% in the horizontal direction, or in the width, and that actually just shrunk it. Notice it's the same height vertically because that dimension is perpendicular, but the dimension this way is shorter, and you see the tires are somewhat elliptical as opposed to circular. The windshield's a little steeper. The whole thing looks just a little less sleek, but it's still a pretty freaking awesome looking car. So, anyways, we have that. Let's see if I can change this to 349. So it seems like whatever mode I'm in this Microsoft Word, it's not letting me do that. So now I finished part A. Now let's do part B. And part B was at what speed must the Aventador travel so that its windshield is inclined at 60 degrees like the Beetle's, and then what would it look like? So I'm going to stop share again. Now I'm going to go back to my document cam. And in part B, it's a little abstract to think of this, but you just take the windshield of, say, the Volkswagen Beetle and compare it. Let's assume that the height of both the windshield and the Volkswagen Beetle and the height of the windshield and the Aventador are 1 meter. You really don't have to, but really what we're saying is we're making a equivalent triangle whose hypotenuse is parallel to the windshield, and basically this length can be anything. As long as the ratio of lengths are right, then the angle will be right. So we want a 60-degree angle. And of course, if this is 1, then we've got to figure out what this would be. And we do tangent 60 degrees is equal to, and of course we already know what the tangent of 60 degrees is. The tangent of 60 degrees is 1.73205 roughly. But that's equal to opposite over adjacent, which would be 1 meter over question mark. Well, that means the question mark here should be, in fact, 0.57735. So I'm carrying way more digits than necessary. Obviously, I only had 2 on my, at best, 2 on my angle. So that's really what the question mark should be there. Now, at the same time, we actually have the Aventador, whose angle is a mere 22 degrees roughly. And if we made that 1 meter, then what would be the question mark here? Well, we say the tangent of 22 degrees is actually equal to, in this case, we found the tangent to be equal to 0.4026. And again, that's also equal to 1 meter over question mark. And this time, question mark turned out to be, and this time, question mark turned out to be 2.475 meters. Okay, so now we know what we have to do. This 1 meter is not going to change, so we don't have to worry much about that. But what I really need to do is I need to take this 2.475, and it's actually 2.4751 meter, and I need to Lorentz contract it or length contract it until its size is 0.57735 meters. Okay. So that's easy enough. We know how to do it. We did the same thing before. We're just using different parameters. So we know that gamma is actually equal to, according to what we did last time, L0 over L. Well, L0 is supposedly the actual length. And remember, the windshield's not really 1 meter tall, nor is this part 2.475 meters. But the windshield would be like a small part, like right here, say, and then the rest of that's just a similar triangle. So in this case, we're going to say 2.4751 meters over 0.57735 meters. Again, we're carrying a bunch of extra sig figs here. With that last one, we really carried 3 as well. When I carry out that division, I end up getting 4.2870. Is actually equal to gamma. Again, that's greater than 1, so that's what we expected. That's a good thing. So now that we know that, we can figure out what beta is. And beta, of course, using our result that we found in Special Relativity 002, is gamma squared minus 1 over gamma, which is actually equal to the square root of 4.2870. Again, we're really carrying 3 extra sig figs there. Squared minus 1, all that divided by 4.2870. When we carry that division out, we end up getting 0.97241. So that's the actual beta. And of course, V is equal to beta times C. So our velocity is going to be 0.97241 C. Again, that can be equal to 0.97241 times 2997992.458 meters per second. Again, me just being obsessive compulsive there. And I end up getting a velocity of 2.915 times 10 to the 8th meters per second. Remember, the speed of light is about 3.00 times 10 to the 8th. So we're really, really approaching that now. And just for completeness, I'm going to add to that in millions of miles per hour, the velocity is 652 million miles per hour. So the Lamborghini, of course, would have to go quite fast to make its windshield be at roughly the same angle as that of the Volkswagen Beetle. Now, what does it look like? That's the other part. So I'm going to stop sharing, or I'm going to start sharing my screen again. I'm going to show you rather quickly where I got this from. So let me click on that. So these schematics that I'm using are, we're fortunate enough to actually have them, because it turns out, actually, I did not go to the right one, did I? Nope, I did not go to the right screen. Stop share. Let's go to the right screen if I can find it on there. That looks like it. Okay, so now I'm on the correct screen. And you'll see this is the actual website that I'm using, www.dimensions.com/element Volkswagen Beetle Type 1. And it gives you, this cool data that I found plus that. And I can literally just take a protractor, complete this line all the way down to here, and then use this as the center of my protractor. And I got 60 degrees for that. Similarly, the same website had the Lamborghini Aventador. And the Aventador, of course, looks like this. And again, if I just complete this line, it ran way over to here. And then I took that angle. That was right around 22 degrees, plus or minus. So that's the website that I was actually using to get that. Let me stop sharing now. And now let me go back to my actual question. Not that one. There it is. And I will show you what the Volkswagen Beetle looked like. Hopefully it'll fit in the screen here. So here was the case in part A when I just made them the same length. In other words, I shrunk the length from 4.78 meters to 4.08 meters, and that's how it got length contracted. Notice this dimension didn't change at all, only the horizontal did, and that took not 249 million miles per hour, but 349 million miles per hour. Sorry about the typo there. Now this one is the pain in the butt because it keeps not showing the thing at the very bottom, which is, in my estimation, the most important part, which is that Volkswagen Beetle. So let me try to view this. Let's see the edit document pane. Okay, that looks a little better because you can see all of them. It's just way too small, and it won't allow me to zoom in on it. But I can do this now. So let's see. So what I've done now is I've taken the actual Volkswagen Beetle and the Aventador and put them on the same scale. In other words, whatever scale this is, then when I take this length from here to here, which is 4.78 meters, and I can divide that length from here by the one from here to here, then I get the same as doing 4.78 divided by 4.08. That's the same ratio. So now these two are actually on the same scale, the Lamborghini and the Volkswagen Beetle. Supposedly have all of them centered, and it looks like I do. Yeah, so that's good. And you can see now that on the same scale, notice the steepness of the windshield. It doesn't look like that, but actually when I measured it, it actually does come pretty accurate, pretty darn close to being the 60 degrees. So that's fairly accurate, but that's what the Lamborghini Aventador would look like if I compressed it until its windshield was about the same steepness. Again, it doesn't look that way here, but when I measured it, it actually came out. But when I measured it along that, I did get 60 degrees, which is roughly the same as this. Of course, it's even boxier and uglier than the Volkswagen Beetle when you're going that speed. But it's kind of interesting that you can actually do that. It's also fun to play with this. Now, to do this, I had to first find out, uh, what the ratio of 4.78 to 4.08 was, and then I compared this length to this length, doing that same division, and from that, that gave me a percentage, and then I multiplied this using the locked aspect ratio, multiplied that by the certain percentage so that it would actually come out to be the same on the same scale as the Volkswagen. Then I just had to compute what the Lorentz contraction was. Lorentz contraction was a factor of 4.2870. If you do 1 divided by that, you'll find that that's about 23.3%. So really, I had to take and reduce this another 23.3% smaller than this because I'd already done 85% to get to be on the same scale as the Volkswagen Beetle. But now I unlocked the aspect ratio and just did the horizontal and changed it by point. When you multiply 23.3 times 85%, 0.233 times 0.85, you get basically 0.199. So it's about 20%. So that's really what's happened here. It's about 20% the length that it would be. And being 20% the length that it would be, you get roughly the same steepness of the windshield. That's it. A lot of technical details on how to do that scaling thing. But anyways, that's not necessarily the physics part of it. The physics is really the actual numbers that we calculated and the concepts of how to make them look that way. I hope that helps everyone. You have a good day.